I'm going to cover in this part essentially matrix computation method that is going to be very useful, not directly with data analytics, but usually in the pre-processing part. In other words, if you recall, we'll talk about, we have a bipartite graph between movies and actors. If you wanted to analyze just network between actors, we have to compute, this kind of movie sharing connectivity. So that's sort of like computation that requires matrix computation. And so once you get that, then you can perform data analytics. So the matrix computation that I'm going to cover, fairly briefly in this second half of the class is some of the more, I guess, useful or powerful tools that you should equip yourself with. Okay. Now, first of all, again, this is from my draft textbook. So that's under graph theoretics. Now we talked about the part one yesterday, and we talked about centrality analysis, right? So yesterday we talked about this and centrality analysis, and this is the bit that I'm going to cover right now. So let me go back and just create a separate workbook here for that. Okay. This code here in blue is just, I give it to you. It's a little bit tedious. It has a lot to do with formatting. Okay. Like I said, mathematics is very powerful and it's decorative. So you can ask it to do something and in one line or two. But what gets tedious is the formatting. And this is sort of like one of those things. So I'm just going to give this to you. So this is a function called, I guess, downward plot weighted adjacency graph. What it means is that if you have a weighted adjacency, right, connectivity between entities, and I want to show sort of like hierarchical of who drives who, and I want to reflect the weight of connectivity in terms of thickness, this is going to be useful. But we'll see how it's used. Okay, but basically inside this, it's based on this thing called layered graph plot, but it has other things like nice colors and so forth. So this is all like formatting. Yeah, but basically it's what's called layered graph plot. So if I press 1, so that's what this is, just layered graph plot. Okay, so you can imagine that this is what I want to do. Okay, except I want to represent hierarchically with colors or thickness of the arrow representing how much weight. So no big deal. So you can just use layered graph if you don't want to worry about this. Right. Okay. First of all, there's this thing called matrix power. Well, matrix power is nothing more than power of matrix. Okay. So a to the power 3, that's a times a. Well, if the matrix is square, you can keep multiplying by itself 3 times, right? So that's what it means. Okay. So let's say if this is my matrix. Okay. So let's say this is my matrix A, B, C, D, right? And I apply matrix power to it, and P is the number of multiplication going from 1 to 4. So let's do that. That's it, right? So this is my matrix. I put in matrix forms. It looks nice. So that's nothing to this. Okay. So to the power 2, fine. To the power, so you can see that. So A, B, C, D times A, B, C, D, you get that. To the power 3, to the power 4, it starts getting big, so it's a little bit unwieldy. Anyway, I want to do the same thing, but now I put real number to it. Okay. So instead of A, B, C, D, I have a matrix of 0.1, 0.2, 0.3, 0.4. Now, you will notice that because the numbers are less than 1, anytime you have number that's less than 1, that's a positive number less than 1, multiplied by positive number less than 1, it gets smaller, right? And that's exactly what happened. Okay, multiply 3 times. Now I add a pen number 100 here so that the choice of power. So if I take this matrix and multiply by itself 100 times, this is what I get. Okay, So you get something very small, very small. So it's 2 times 10 to the minus 28 or something. Okay. So that's all it is. That's what it just multiplying by itself that many times. Okay. It's written as a matrix power, just a summary. Now here's where Mathematica becomes powerful. What if I want to do this to infinite time? Okay, now you can't do this with normal programming language like Python. You can do 10,000 multiplication, but you can't do infinite. Well, in Mathematica, you can say, I want to take this power p times. And I tell Mathematica, again, decorative, I want p to go to infinity. Okay, now this is not surprising. What are you going to get? What do you think it's going to get? Well, if 100 times get you to 10 to the minus 28, what do you think infinity number of multiplications is going to get you? I'm just going to get you 0. Oops. Enter. Just basically just approaches 0. Okay, it just vanishes. It just vanishes. No surprise there. No surprise there. Okay. Now, here's where it gets interesting. We have had a project. Again, this is Bombasai in partnership with Business Online. Because we detail, I have a detailed write-up about it here. This is actually in a Basai blog, right? Web blog. I don't know if you read this one, but it's one of the faculty blogs, and talks about a little bit about the project and the rationale. Anyway, let me give you the background. The background is like this. Normally, right, a company makes money, that's revenue. Okay, it makes profit. That profit gets taxed. That profit gets taxed. The more revenue you have, the more tax you have to pay as a fixed percentage, say 20%. Now, imagine that because of some regulation or some kind of you're familiar with this, individuals have different tax rates depending on bracket. Well, corporate also have that kind of thing. So maybe because of a special tax status, instead of being taxed 20%, it's taxed 10%. Okay. Now, normally this doesn't matter because, you know, you make money, you get taxed. But what if 2 companies are jointly owned? So literally there are 2 companies, one gets 20% tax, one gets 10% tax. But actually, even though they're separate companies, you own both. Okay? You own both. What is the motivation? Your motivation is to do this. You are going to try to hide the profit in a relatively high tax entity, 20%, make that one unprofitable, and take the profit from there and stick it in a low tax entity, right? So if I have $1 million worth of revenue, if there's a mechanism where I can actually allocate 0 of it to the company that I own that pays 20% tax and have all the profit allocated to the company that I own that pays 5 or 10% tax, right? I'm going to get a lot of tax saving, right? That's 100 million times 10%, right? So that's 10 million easily. Okay. So this is kind of like tax evasion, it's tax cheat. Now, normally this is not easy to do. You can't just take profit from company A and stick it to company B. It turns out that sometimes company A and company B are part of a chain, like a supply chain. You know what a supply chain is, right? So it's not just companies selling to you, but companies selling to companies. So A can sell some intermediate goods to B, and B can then sell it to you. The point is that sometimes the price that A and B charges each other is not something transparent. Okay, there's no market index. For example, if A makes half a car, okay, sell it to B, B makes the other half and sell it to you. There's no market price for half a car. Okay, so somehow they have to put it in accounting, and that's where tax cheat comes in. When that thing is called transfer pricing, it's price for transferring items or profit from one company to the next. And by manipulating the transfer pricing, I can make one company looks weak, makes no profit at all. The other one strong, makes a lot of money, and that one pays tax. So anyway, the idea here is that it's very hard to determine what's happening. So with the BOL, and this is a project that Chulalongkorn or I team with the business did for revenue department, which is, to find the relationship, try to find the relationship between companies. And so if you think about it, finding relationship company is a little bit like matrix computation, right? Because after all, if instead of saying that I know this, you know this guy knows that guy, or Kevin Bacon acts in the same movie as Bruce Lee, or not in the same Bruce Lee as movie as Bruce Lee. Instead of having that, we can have ownership graph, right? Ownership graph. Now, here's the thing about ownership graph. Well, I just draw a little picture here. If this company owns this company, it's obvious, right? How do I know that? Because this is, well, by the way, these are all like a public information, right? So let's say a public company has to list the shareholder. So let's say this company A or you owns 60% of this company. So 40% from somebody else. Okay, right? That makes sense. Fine. You can imagine that all this holding between company is one matrix. So it's A, B, C, D, E, F, G, and A holds how many percent of B? 60%. Okay. The point is that, what about C? What if B owns, say, 80% of C? Okay, but A doesn't own anything. If you look at this, it's gonna look like A doesn't have any influence whatsoever, right? Because A cannot influence C, A doesn't own C. However, because A owns 60% of B and B owns 80% of C, effectively A owns, well, let's make it 90, sorry. Effectively, A owns 54% of C. It actually can control C. So even though here on this thing, it looks zero, it has control. Okay. Well, you can imagine that this can keep going, right? So what do you think is happening? If this here is represented by a matrix, the second line is represented by matrix square. So matrix power. What about here? It's matrix cube. So if I want to consolidate, how much who owns who in a company, what I need to do is have this plus this square plus this cube plus this fourth plus dot, 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 dot. That looks like very important, very difficult, right? Now, in the limit, we did this for 0.1, 0.2, 0.3, 0.4, but that's easy. It's only 2 by 2, right? Well, in Thailand, there are at least 100,000 companies. So let's say we're working with 50,000. That's 50,000 by 50,000 matrix that I have to square. Well, it turns out that you don't have to go very far. Remember that it goes to zero real quick. It turns out that by the time you go to maybe third order, you've covered most of it. So that's not that computationally, that's not that scary. So let's see how this is done. see how this is done. Well, it's done in the takeaway number 13. So I'm going to make artificial, and then I have to make this artificial. And to make it interesting, this is what it looks like. Oops. Okay. Now, you guys remember the sparse matrix we talked about, right? Well, it doesn't have to be sparse matrix, but it's easy for me to write. What it means is that there are 4 companies, 1, 2, 3, 4. 1 owns 60% of 2, and 60% of 3. 2 owns 40% of 3. 2 owns 6% of 4. 3 owns 40% of 4. Now, that could be some kind of like, loop back, but to make it simple, and it tends to look like this, kind of downward. Because this is something like, this is a parent company, this is subsidiary, subsidiary has subsidiary. Now, obviously, subsidiary can own part of parent company. Okay, that happens. It's legal, but it just complicates the picture. So, okay, so I'm going to make it strictly downward. So 1 owns 2. So this is what it looks like. Okay, so I create this matrix. So that's my matrix. That's 4 by 4 matrix. I turn this into adjacency graph, but again, unlike yesterday we did this. We turned graph into matrix, matrix into graph, right? Now I added the word weighted because I want it to be weighted. Now I can actually just put layer plot here, but this is the special function that I gave you so that it adds color. It looks nice. Yeah. Not only does it add color, it labels the connection and all that. It's just nice. Okay. Right. So notice the thickness as well. The thickness is proportional to the size. So 1 owns 60% of 3 and 2. 2 owns less than 60% of 3. Oops, 2 owns what? 40%. So the number gets smaller. So different color and thinner line. Okay, fine. That's the first shot. Okay. So what happened when I want to consolidate? Now notice, oops. This is like that picture, right? 1 owns 2, 2 owns 3, but 1 also owns 3. But the thing is, 1 doesn't just own 3 directly, it owns 3 indirectly. So there's another thing. Moreover, like the example we saw, 1 doesn't own 4. But actually, this times that is how much 1 owns 4, right? And not only that, because 3 owns 4, how much does 1 own 4? It's this channel and this channel as well, right? So we have to calculate all that. And this is where matrix computation comes. So let's do parent to grandchild. So this is it. Okay. Now, this is just matrix square. Matrix square. Okay, matrix dot matrix. So that's power 2 basically. Okay, so you can see that 1 owns 3, 1 owns 4, 2 owns 4. Okay. So obviously it's the same thing. Instead of doing this, I can say power matrix. Sorry, matrix power. Matrix pose. And 2. Oops. Same thing, right? Fine. Well, now I don't want just power. So this, notice this is a critical one. Okay, you make it larger. Right. Watch this. Matrix power ownership to the power P. Okay. I apply this to range 2. So what does it mean? Range 2 is 1 and 2, right? So this applies to, so what I'm going to get when I apply this to range 2 is I'm going to get matrix, comma, matrix square. Now, I don't want just matrix and matrix square. I want to add them together. So I put total, right? So what it is ownership matrix to the power 1, ownership matrix to the power 2, add them together, turn that into a graph, and then show it. Okay? So basically, it's this graph plus this graph. Okay? Now, just to be sure that you see that it's exactly the same thing, I can say ownership matrix plus ownership matrix times ownership matrix. So this thing is the same thing as total of matrix power 1 and 2, right? Just want to show that it's the same thing. Now when I write the text, I have to sort of like spell everything out. So let's look at what happened. So now instead of summing from 1 to 2, I'm going to say sum from 1 to 2 to 3, and maybe to 100. Okay, make it medium. Okay, so this is basically the first one we saw earlier. If I want to add to 2, I get this. So that's what we saw earlier, right? Now, if I want to add to 3, let's make it small, sorry. 3. Notice that nothing changes. Topography doesn't change in this case. Between 2 and 3, what changes is that long line between 1 and 4. Because if you recall, right? Original ownership, how do you link 1 to 4? 1 connection, 2 connection, 3 connection. So it takes 3 matrix multiplication before you get effect. Okay? It gets 3 multiplication before you get total effect. And so you get this. Now, once you get to here, other effect doesn't, it just sort of like dies down. So basically, that's the thing. Okay? In fact, now this is just to prove that, yeah, this is the difference. I take the difference between yeah, 100 and 1. There's a difference, right? And if I multiply 2 times and add them, okay, versus 100 times, that's a difference. By the time you get to 3, there's virtually no difference. So basically, you don't have to keep adding. So that's like a good news. You don't have to go to infinity. However, having said that, going to infinity is not that difficult. Remember, eigenvector, system is the same thing. It's multiplying by infinity recursively. Okay, so that's what happened. Now, you recall, right? You recall that with bipartite graph, you have to know this. By the way, I'm going to ask you about bipartite graph on the exam. There's actors on one side, movies on the other. Okay? Actors on one side, movies on the other. Okay? Now, in this case, what if, let's do this. Let's say that still have 4 companies like before. 4 companies. But we add 2 guys. 2 guys. Okay? 2 guys. Right? The idea is, well, in this case, I don't want to connect company to company using that Bacon number calculation. I just want to look at how much they are together. So if I own 80% of A and I as a person own 80% of B, so this human being owns another company, 80% and 80%, chances are I can make them do whatever I like. Okay. Now, technically, this doesn't have to be bipartite. I could be another company, but just to make the example clear, you can think of 1, 2, 3, 4 as companies and 5, 6 as a person. Okay. But before, so the idea is to sort of like consolidate horizontally. Okay. So this is a bit like that movie actors and, you know, where you have actors go to movie and back to actor. Okay. But before I get to that, I want to introduce to you something that is extremely powerful. It's called inner operation. Okay. So just now, the mathematics is called matrix power, but that's nothing more than matrix square matrix multiplied by itself. Okay, that's not that. But this one is very important. This is called inner. Well, what's inner operation? What's inner operation? Okay. Let me draw a picture. Do you guys remember dot product? You guys remember dot product? Right? So what do? You have two things that have the same dimension or same length, basically, right? You take element by element, each pair, you multiply, right? And then you take this one and you multiply. So you have a list of things and you have a list of things, and then you make a list of things pairwise multiply, and then you add them. Okay? So remember those two words? Pairwise multiplication. Then the whole string gets added together. Okay? Okay. So this, well, right? Oops, I have to stop this one. Yeah. This is my dot product, right? Right? This is this is my this one, this is my dot product. You see the dot, right? Right? This is one, right? So what essentially happens is A1 times B1, A2 times B2, and A3 times B3, and then you add. Okay? An inner operation is a generalization where I can do anything here. So instead of saying I'm going to do a dot product, I'm going to do an inner operation involving multiplication first and then addition. Does that make sense? Right? So a dot product is an inner operation where the first kind of operation is pairwise multiplication. Second operation is addition. Okay? So just to make life so dot product is equal to inner operation with multiply first, then add later. Does that make sense? That makes sense? So that's how I write this. An inner operation between this guy and that guy, time is multiplication, right? And plus is plus. Okay? So that's why it's the same thing. I say inner operation times and plus is the same thing as the dot product. Okay. Oops. All right. Now, why would you do this? Obviously, if you have common sense, it's so that I can do something else. Right? In fact, this is what I want to show you. Well, first of all, again, a dot product, okay, and by extension matrix multiplication is a special case of inner operation. So I can do vector at dot product. I can do this, the same thing, right? What's this? This is a 2x2 matrix by vector of dimension 2, right? 2x2 times 2x1, the same thing. So what's this? What's matrix and matrix? So this is just checking that, yeah, it does do the right thing. Okay. So the dot product here is essentially a specialized form of this. The specialization is the first thing you do is times thing together, multiply. The second thing you do is plus thing together or add, right? I don't know why I use that word. It's kind of awkward anyway. But so if this is times and plus, what if we did the opposite? We plus first and times. What do you guys think is going to happen? It's going to get binomial expansion. Right? Yeah, because it takes the first two elements, plus them first, second element plus them, third element plus them, and then times them. Okay, this is an operation. It's completely valid. Completely valid. It serves a different purpose, but it's completely valid. Okay. What else? So this is one of those tools that เดี๋ยวให้นัดหา equivalent ใน Python หน่อยก็ดีแต่รู้สึกจะไม่มี Okay. Well, I can do all kinds of things. I can do divide and plus, so that's it, right? So this is kind of become silly now. I can do all kinds of stuff. Now, here's where it gets interesting. That operation does not have to be mathematics. It could be any function. In fact, well, I'm going to use built-in function, but you can use this minimization, not minimum. So you can take the minimum of A1 and B1, minimum of A2 and B2. Right? Now, obviously, you don't know what A1, B1 is, so I'm going to add some number to it. What do you think it's going to get? Okay. I can ask this on an exam if you like, because this is simple, right? What should this give you? Take the first pair. The minimum of that is 1. What's the minimum of second pair? 2. What's the minimum of third pair? 1. What do you do with 1, 2, 1? You add them. 1 plus 2 plus 1 equal to 4. Right? Likewise, power. Now, why do I give you this example, by the way? This example appeared in my thesis. I was doing what's called evolutionary optimization of a trading model. Today, we call it algorithmic trading. That was my thesis. So, well, not the whole thesis, but the big chunk of my thesis was algorithmic trading, algo trading. But I didn't have one model. I have ensemble of model. I didn't have ensemble of model. I have ensemble of different classes of model. So you can think of one class of model takes 5 parameters. The other class takes 10 parameters. And I have 2 of that first class, 3 of the second class. The question is, if I were to do a grid search, literally find all the parameters that works best, give me the most money, then I was I was in intern at quantitative research trading chemical bank in London, and they were doing FX trading. So if I were to do that, D is the dimension, the number of parameters needed for the first class of model. N1 is the number of those. D2 is the dimension or the number of parameters for the second class of training signal. N2 is how many of those I use. So if I did this, by the way, I do an optimization search, I don't just run them through. The number of search, in other words, space itself is n to the power d to the n1 times d to n2 times d to the n3. Okay. Now, interestingly, the power just means take the first one raised to the power second one. So that's the same thing as this, right? If I want to write it as a pure function, okay, this is the same thing, right? Take the first one raised to the power second one. So see, that's the same. Find the mouse. Where's my mouse? Okay. So this is that. The same thing. Right? Same thing. Same thing. Now, what's cool about this is that now what if I just write this number 2? That means I ignore the first guy. Right? And finally, just to be fun, just for fun, this has no application I can think of right now. What about raise to the power and then raise to the power? What do you think comes up to? Right? So A1 to the power B1, A2 to the power B2, A3 to the power B3, and all of them raise each other. So you get like this little. Yeah. So that one just for fun. Okay. Well, here's the thing. Here's the thing. This is what I want to do. This is my matrix. Aha. Right? Company. Now, these two, like I said, could be company, but for now, think of them as a guy. Yeah? A guy owns this much of this, this much of this, this much of this, this much of this, this much of this. So I want to consolidate laterally, as if this were actors and this is movies. But instead of counting how many times, what I want to do is take the weight. So imagine, now in this case, here's the number. Here's the number, okay? A guy named 5 owns 70% of company 1. A guy named 5 also owns 60% of company 2, right? A guy named 5 also owns 50%, like this. Now, again, I want to know how much these two companies are connected laterally. Okay, this is called horizontal integration. And this is actually spelled out by law. Okay, it's called disclosure transfer pricing law in the Kingdom of Thailand. Company has to calculate this. Well, company just has to look at the company. We want to look at the whole system. So we have to look at all the companies together. So I want to know how much is one linked to 2, how much is one linked to 3, how much is one linked to 4. Basically created a weighted adjacency matrix. Okay, how will I do that? Well, first of all, what's the criteria? I'm going to show you here 2 criteria. One method would be something like this. How about 1 and 2 is linked by multiplying the weight together. So 0.7 and 0.6, right? Or I can say something like, well, this is a guy, he owns 60% of this, 70% of this. So somehow the minimum influence he has is actually the minimum of 6 and 7, 60 and 7. So it's actually minimum of the 2 number. Now you can see why that in the operation comes in handy. So in order to do this, all I need to do, and this would be algorithmically very difficult if you were to do this using something like database programming, SQL. It would take you huge amount of programming, but here is one line. Okay. Now, first of all, I don't want this. I want a bipartite version of this. Remember, bipartite is just companies on one side, people on the other. So I just take this. So that's what it looks like. Okay. So 5 owns 70% of company 1, 60% of company 2, 50% of company 3. 6 owns 40% of company 2, 30% of company 3, and 2% of company 4. So this is a bipartite, right? So guy on one side, and I want to create a 4x4 adjacency matrix, weighted adjacency matrix, linking 1, 2, 3, 4. And how would I do that? Well, if the criteria is to multiply, all I do is just transpose this and multiply. Yeah. That's it. That's it. So this is how you can link. For example, look at this guy. Look at my hand. Guy number 1, sorry, a guy named 5 owns 70% of company 1 and owns 60% of company 2. And there are no other links between 1 and 2. So this is it. This is it. If I want to multiply them together, it's 7 times 6 is 42. Okay. Now, the middle one, that's irrelevant because that's the same company. So I'm going to remove that diagonal later. But you can see that this is 42. How about 2 and 3? Let's work out 2 and 3. 2 and 3 is 60 times 50. That's what? 30%, right? But you also have 40 times 30. That's 12 more percent. Is that right? Okay, so 12 more percent. So that's 2 and 3. There, that's 42. Okay, so this is 42, this is 42, but they're different 42. This 42 is 7 times 6. This 42 is 6 times 5 plus 4 times 3. Okay, so, and just to convince you that it's the same thing, I make the transpose of this and multiply. It's the same thing as inner times plus. Finally, here's the kicker. What if I don't want to multiply? I want to take the minimum of 7 and 6. Minimum of 6 and 5, 4 and 3. I simply replace this word times with the word min. Again, if you want to do this professionally with SQL, it would take you maybe a page. I don't know. I'm not a SQL programmer. Okay. Now, this is just a little thing that I use to remove that diagonal. So that doesn't really mean much. So here it is. Okay. So I just removed the diagonal. So immediately now I have the lateral connectivity between companies based on multiplication, based on minimum. Oops. Okay, this is the multiplication. Go down here. Ooh. Sorry. Wrong. Okay. This one is min. There. Okay, sorry. Almost. Okay, so this is the same thing as above. So multiply, but this one, instead of adding multiplying, you take the minimum. So minimum of 6 and 7 is 6. Okay. What about the other channel? Minimum of 5 and 3 is 5, and minimum of 4. Minimum of 6 and 5 is 5. Minimum of 6, 4 and 3 is 3. Add them together, 5 plus 3. Eight. So this inner operation is very powerful for manipulating this. And I can do all kinds of stuff. But for our purpose, I can do this thing. So maybe, I can do even weirder things. I can, for example, imagine that take the first company is more important than the second company, but okay. But this already is powerful. Okay. And this is actually something that has to be done by law. Except in real life, if you didn't have this operation, you would use SQL and it would take you a while. I don't mean computationally, it takes you a while to write the codes, okay? Whereas this is just one line. So anyway, so based on this is the blog that I wrote, and it's in the Basai blog, and so forth. So with that, I think I'm going to try to cut short today again and give you time to do the whole exercise yesterday. Now, yesterday I did log in to listen to you guys, so I don't know what went on. But again, remember, 40% paper, data visualization, 20% supervised learning, 20% unsupervised learning, 20% video, because this is Basai. And I think that's about it. Okay, so anyway, I'm not gonna save this. Oh, maybe I should say. Aside from the last one where I didn't write times, okay, this is I might as well do it again. Okay. And I'll give it to you guys again in the line group, all right? Class takeaway 13. Okay, let me unsend this one. And this thing that I asked you to copy verbatim, that's in here as well. That's okay. So that's that. Okay. So you guys can take a break, take a breather, and then I'll let you take over and do the same thing. Now, next week, let me tell you what happened next week. Next week, yeah. Right. Yeah, we talked about a lot about this and big data, right? That's V. We don't do this V, we don't do this V, we do that V. That V is for variety, right? So first we have categorical, yeah, that's fine. We have graph, okay. Then we're gonna have picture and words. So these two, we'll talk briefly about how we do machine learning with that. You can't do probabilistic or statistical model. You can in some case, like word count or something like that. Okay, so let's say word. Okay, word. Now, in the old days, people at wartime, they would use word substitution. So instead of saying, march your cavalry to the right on the east of the mountain, okay, they'll use a word like chicken for mountain or something like that, okay? Or now that's not very sophisticated. You can figure out soon enough what that chicken means a mountain. So next thing you do is called alphabet substitution, right? So A, B, C, D, E becomes something like H, K, M, L, Q, right? So if I want to go to mountain name ABC, I'll say I'll go to mountain KHM. Okay, right? So you can't read what the meaning is. That's called word substitution. It's a cipher, but that's easy to solve. You know how? Because in a typical language, there's a distribution of A That's a distribution of B. That's a distribution of C. So you can actually, even though you're using the word K every time you see A, it's going to have probability same as probability A. It's this kind of thing. So you can do probabilistic modeling on text to do this kind of thing. Okay. We are actually going to do much better than this. We're going to do much better than this. How? Just like I can represent graph on an embedding, I can represent 15-dimensional vector in 2-dimensional dimensionality reduction exercise. Remember that? What's the criteria? Things that are close together in 15 dimension appears closer in 2 dimension. Word embedding is the same thing. Words that appear closer, not in 15 dimension, but in English language would appear closer in an artificial dimension. Now, the magic number they use is usually something like 300. So they're not going to plot this. Okay. But essentially, what it does is it maps word into a vector. So you map the word king into V. You map the word queen into V2. You map the word boy into V3. Map the word girl into V4. If you did this well enough, you can say that queen is a girl king. Does that make sense? How do you do that? Queen V2 is equal to V1 king minus boyness at girlness. Okay, so the data analytics here to deal again with variety of data. Now you want to deal with words. You can't deal with words until it becomes number, but you do it in such a way that it's a clever scheme. And this is called word embedding. Okay, this is the basis. Once you have this word representation as number, you can do machine learning, you can do all kinds of stuff, and that's how you get chatbot. Right? Because you can say something like rain minus umbrella equal to wet. Okay, chatbot AI cannot talk to you because you speak English. The reason you can speak English to AI is because English has been turned into vectors. Machine learning learns from vectors and then talk to you. Yeah. So talk a little bit about that in principle, not in detail. And finally, picture. And all I'm going to say is this. Instead of having picture, you turn this into number, right? And you do what's called filtering. So you detect vertical line, detect horizontal line. So you can imagine that a cat is a vertical line, 4 of them means leg or something like that. So it's that kind of thing. Okay. So this is called convolutional learning or convolutional neural network. So this is a final bit that links machine learning. Machine learning, that's the analytics on variety data. Okay, and that's the last bit that you're gonna learn. Then project. Okay, now so I don't want to stay too long because that takes you time from your workshop. Okay, so continue where you left off. I don't know if you went to all of them, but there's more time for you to do that. Okay. Okay. Your grades out, by the way, but your TA is gonna give the individual. So okay, so that's the end of the class today.